Transfer matrix method using scattering matrices. So this is the lecture where everything is going to come together. Up to this point, we've talked a lot about scattering matrices, but we didn't actually say what to do with that global scattering matrix in order to calculate how much of the incident wave gets reflected or transmitted. So we have to cover that. After that, we'll be in a great position really to talk about how to implement transfer matrix method or even rigorous coupled wave analysis method of lines later in this class. But for transfer matrix method, because all these layers are composed of linear, homogeneous, isotropic materials, there's a lot of simplifications that can happen. So we're going to go through all of that. We'll then talk about a bunch of different things on implementation, how to make different steps more efficient. And I'll be throwing a lot of things at you, and it's easy to kind of get lost or confusing because there's not really an order to this. It's just a bunch of things that we need to do more efficiently in the implementation. But at the very end, I present a block diagram where all of this stuff comes together into a nice simple block diagram. So let's get right into this. Calculating transmitted and reflected power. One of the first things we need to do is calculate the source. And so this picture, I'm showing an incident wave, incident onto an interface. And so all the layers would be going vertically in this case. And there's a TE direction for polarization, a TM direction. We have our angle of incidence theta. We have this angle phi off of the x-axis. And of course, we have our plane of incidence. And so that's the basic geometry. Notice the orientation of the x, y, z axes. These have to form a right-handed system. If that's not it, we're going to get sign inversions and problems will arise. In the calculations we're about to discuss, we need the surface normal. And in this case, the surface normal will be pointing downward in the positive z direction. We will need to calculate the incident wave vector. So the magnitude of the wave vector will be the free space wave number times the refractive index where the wave is being injected. And then we also have the x, y, and z components of that. Sometimes these are called the direction cosines because the magnitude of the vector in square brackets here is 1. And the real magnitude of the wave vector is conveyed out here. But this is really how we go from spherical coordinates to Cartesian coordinates. And so that's how we calculate x, y, and z components of our incident wave vector. Now we'd like to know what direction is the TE wave. Well, we have the plane of incidence is defined by the plane, defined by the wave vector and the surface normal. Those two vectors define a plane. That's the plane of incidence, and the TE direction is perpendicular to that. So we can use the properties of a cross product to calculate the direction that's perpendicular to both k and n. And that's exactly what we do. We look at the cross product, and that'll give us the direction of the TE, but that will be polluted by the magnitude of the incident wave vector, or if these aren't at 90 degrees. So what we have to do is divide by the magnitude of that cross product, and that gives us a unit vector in the direction of TE. Now there's one case where that equation fails, and that's when we have normal incidence. That's when our theta equals 0 degrees. And for normal incidence, there really is no plane of incidence. There is no TE and TM directions, and so we're free to define those based on convenience or something else. For my codes, I tend to like to choose the Y direction to be the default direction for TE and normal incidence, but just remember, for normal incidence, there really is no TE and TM, and we can choose any direction there. I will choose Y to proceed with. Given that we have the TE direction, now we can calculate a unit vector in the direction of the TM polarization. Again, we'll use cross products. The TM polarization has to be perpendicular to both the direction of the wave and the TE polarization. So we just take the cross product to do that, and of course divide by the magnitude, so we end up with a unit vector. Given that we have directions in the TE and TM polarizations, we're in a position to calculate the overall composite polarization vector. So this really is the amplitude and the direction of the electric field of the applied wave. and it has some complex amplitude in the TE direction and some complex amplitude in the TM direction. Typically, this P sub TE and P sub TM, these will be inputs to our transfer matrix method to define the polarization of the wave. Then in order to calculate later transmission and reflection, we have to tie all this together into a composite polarization vector, and that's how we do that. One last thing, in anything numerical, we almost always normalize things to be 1. And so we're going to force the magnitude of our polarization vector to be 1. That makes the amplitude of our applied wave 1, and things just work out much more nicely that way. Is it absolutely required? No, not really, but it's good practice. Okay, so up to this point, we now know how to calculate a global scattering matrix. We know how to calculate a polarization vector. How do we use all this to figure out what actually gets transmitted and reflected from our device? Well, let's first look at this picture at the lower right. And so think of this as the black box around our global scattering matrix. So we will have a wave incident from the left. That's our C-ints. We can get a wave reflected. That's our C-ref. We can get a wave transmitted, that's our CTRN, and it is also possible to have another wave incident from the right. Now, I've never actually seen anybody do that, so almost always that's just set to 0. In principle, we could still have that. So since we only have one incident wave from the left, we're just going to call this left incident wave just C-ints. So we only have one incident wave. So we can write our global scattering matrix relating our inputs, our C-ints, and of course we have no input from the port 2 or the right-hand side. So those are our inputs, and the outputs are C-ref and CTRN. So given this global scattering matrix and our incident wave, we can calculate what gets reflected and transmitted. So we have to calculate C-ints. Those aren't the fields, those are the mode coefficients. So in order to go from field terms to mode coefficients, we have to pre-divide by the eigenvector matrix of the electric fields, because these polarization terms are electric field quantities. So given this polarization vector we talked about in a previous slide, we pre-divide by our eigenvector matrix, and we can calculate the mode coefficients of the incident wave. Now notice we're only making use of the x and y components of the polarization vector. It turns out the z component is not needed. And if you want to shortcut that calculation a little bit, you don't even have to calculate the z component of that polarization vector. I normally do, but I just proceed in my calculations with the x and y components. So let's expand our global scattering matrix into the S11, S12, S21, S22. This 0 being here really simplifies how we calculate C-ref and CTRN. So if we expand this block matrix equation into the two component equations, this is what we end up with. So the reflected mode coefficients are simply S11 times the incident mode coefficients. The transmitted mode coefficients are S21 times the incident wave. That's very easy to do. Well, we know the mode coefficients at this point. That's not sufficient. Really, in order to calculate how much gets transmitted and reflected, we need the fields. So in order to calculate the fields from these mode coefficients, we have to pre-multiply by our eigenvector matrices. So if we want the fields in the reflection side, we pre-multiply by the eigenvectors of the reflection region times the mode coefficients of the reflected fields, and we get our electric fields on the reflection side. Likewise, our fields on the transmitted side is the eigenvector matrix for the transmitted side times the mode coefficients on the transmitted side. Now we know the fields. Now we're in a good position to start thinking about actually calculating transmission and reflection. At this point, however, we only have the x and y components of the electric field. In order to figure out what the magnitude of the field is, we need the z component. So how do we get that? Well, that actually comes from the divergence equation. So this forms a rule of how the x, y, and z components are related such that the electric field has zero divergence. So what we can do is we can expand this divergence equation, and we can solve for the z component of the electric field in terms of the x and y components. So this actually is the equation we will use to calculate the z component of the electric field. And of course we can write that twice. Once to get the z component on the reflection side, and once to get the z component on the transmission side. Now we are ready to calculate the magnitude of the electric fields on both sides and calculate reflectance and transmittance. So reflectance. Reflectance is the fraction of power reflected from the device. Since we're talking about power, that's why we have the magnitude squared of the electric fields. So reflected power divided by incident power gives us our reflectance, fraction of power reflected. And since we have the x, y, and z components on both sides of the interface and our applied wave, we're in a very good position to calculate the magnitude of the electric field wherever we want it. Tiny bit trickier to calculate the transmittance. That's because there's some extra terms here. In essence, it is just transmitted power divided by incident power, but there's these other terms here. We have our wave vectors and our permeability, and that's because if the materials are different on either side of our device, even though the power might be the same, if the materials are different, those fields could be misbalanced, and we need to compensate for that. Notice in these equations, we're not really referring to this polarization vector. We have E-ints over here. Well, E-ints is the polarization vector. Perhaps I should put the polarization vector in these equations, but then it might make less sense that it's, for example, reflectance is power reflected divided by power incident. So anyway, E-ints is the polarization vector. Once we have reflectance and transmittance, it's always good practice to add these together. And most of the time, we'll run simulations that don't have loss or gain. So reflectance plus transmittance will always equal 1. Now, if there is loss, then transmittance plus reflectance will not equal 1. It'll be something less. And of course, if there is gain, it's the other way around. Transmission and reflection will be greater than 1. So even if we're simulating something with loss or gain, I think it's always good practice to turn that off, run a simulation, make sure you get conservation of power, then turn it back on, and we can trust our results a little bit more. Very often, we would like to put reflectance and transmittance on a decibel scale. So remember how the decibel scale works. If we have an amplitude quantity, we'll take the log base 10, but we multiply by 20 to give us a power quantity. If we started with a power quantity, it's still log base 10, but we only multiply by 10. And that's because we want to square an amplitude quantity, and that squared comes out and doubles that 10 to be a 20. So depending whether we're calculating our power from an amplitude or power quantity, we would multiply by 20 or 10. And this is very easily confused. Reflectance and transmittance are power quantities, so we always use a 10 log 10. Don't use 20 log 10 here. Now let's discuss simplifications of the 1D transfer matrix method. Let's talk about our first simplification. It turns out our eigenvector matrix W and eigenvalue matrix lambda we can calculate with analytical expressions, and they're super easy. We don't have to call eig, and that's really neat. We certainly can call eig, but we don't have to, and that makes our code run a little bit faster. So let's remember what the dispersion relation is in LHI media. Now, we've written it here. And these are with normalized wave vector components. That's why there's not a k0 squared sitting over here. So file that away. Now let's look at our omega squared matrix. Up to now, we're thinking in our heads, we're going to build the P matrix, we're going to build the Q matrix, we're going to multiply them together, and that gives us our omega squared matrix, and then we calculate eigenvectors and eigenvalues. Okay, so here's what that would look like if we multiply P and Q together. Now, armed with this dispersion relation and a lot of algebra, something really neat happens. This becomes a diagonal matrix with minus kz squared in both the diagonal positions. That means if we wanted omega squared, We could build it just by calculating minus kz squared times an identity matrix. That's pretty neat. Well, it gets even better. It turns out if we calculate the eigenvalues and eigenvectors of a diagonal matrix, the eigenvector matrix is an identity matrix, and the matrix we had to start with is our eigenvalues. So our eigenvalue matrix squared is omega squared. If we take the square root of that, it's a diagonal matrix, so that's trivial. The square root of negative kz squared is j, or the square root of negative 1, times kz. So we can build that directly just as jkz times the identity matrix. So we really don't even need to build p and q and call eig. This becomes very simple and trivial. What lets this happen is we're talking about linear, homogeneous, and isotropic materials. So if we take the exponential of that now, that's easy. It's a diagonal matrix. So we just take the exponential of these two diagonal elements, and now we have our exponential of the eigenvalue matrix. More useful things happen. So here's where our conclusions from the previous slide. Somewhere along the way, we need to calculate the eigenvector matrix for the magnetic fields. Well, this was the equation we had when we did that. However, since all of our W's are an identity matrix, that falls out of the equation. So we have a little bit simpler equation for calculating the eigenvectors for the magnetic fields. When we calculate our scattering matrices, we have these intermediate parameters A and B, and we have products of W's and products of V's. But if our W's are all identity matrices, these equations reduce and the W's just fall out. In fact, in the transfer matrix method, W is not used at all because it's the identity matrix. Another really cool thing we'll also talk about in a little bit, the mode coefficients are the same as the fields. Remember, we convert back and forth through the W matrix. If the W matrix is the identity matrix, the fields and the mode coefficients are the same thing in our transfer matrix method. Our expressions for the reflection side and transmission side, scattering matrices that connect us to the outside world, these simplify a little bit because the W's are the identity matrix. Now let's get into the implementation. This is going to be a random mix of a bunch of different things, and we're going to tie it all together with a block diagram. Now in written form, here's what we're looking at to implement the transfer matrix method. So step 0, we're doing this on paper, we're doing this ourselves. We're defining the problem. What device is it we want to simulate? What are the material properties? What are the dimensions? What do we want to learn? Then finally in our code, in step 1, we have our dashboard. This is where we define everything about our device. All of the hard-coded numbers are in the dashboard, and we don't do any work there. And we know we've done a good job of the dashboard if I come back and ask, okay, that was a good simulation, but now change the dimension of one of the layers. If you have to do anything other than change that number in the dashboard, you're doing something wrong in your code. So we define everything in the dashboard. Then we go on to step 2. We define the device layers, and we'll store the material properties and layer thicknesses in arrays. So we'll do all that. We then go on and calculate our wave vector components. We know we need that for calculating scattering matrices and later on the transmission and reflection. We need to calculate our gap medium parameters because all of the scattering matrices will need that. We'll then initialize the global scattering matrix. At this point, we enter into our main loop where we iterate through all of the different layers. And so for each layer, we'll compute P and Q, compute the eigenmodes, compute the layer scattering matrix, we'll update the global scattering matrix, and we do that for each layer. When we're done, we then connect it to the outside world. So we'll calculate the reflection side scattering matrix, transmission side scattering matrix, and connect those on with another Redheffer Star Product to the global scattering matrix. Now we're ready to analyze things. We'll calculate the source. This is the polarization vector, TE, TM directions. We will calculate the reflected and transmitted fields. We'll then calculate reflectance and transmittance, and we will verify conservation of power because that's always very good practice. Now later on we'll put this in block diagram form, but I wanted to pass through this just to put what we're talking about in subsequent slides into some better context. So how do we store the problem? Somehow the computer has to know what it is we're simulating. And so we always have a right-handed coordinate system. That's what we're showing here. And we know it's right-handed if we do a cross product of the x direction with the y direction and we get the z direction. So let's say we have 3 layers that we want to describe. Each layer has 3 numbers associated with it. It has a permittivity, relative permeability, and a thickness. And the thickness will be done in terms of wavelength because they're normalized numbers. So we will store all the permittivities in an array. So it's an array with 3 numbers in it. We'll store all of our permeabilities in an array with 3 numbers, and we'll store all of our layer thicknesses in an array with 3 numbers. If we had 100 layers, we would have 100 numbers in these different arrays. So that's how those are stored. Now we also need to know the external materials. We'll just define these as constants up in the dashboard. But we'll have ER1, that'll be the relative permittivity in the reflection region. UR1 will be the relative permeability in the reflection region. And ER2 and UR2, that's the relative permittivity and permeability on the transmission side of the device. We will need to know about the source. So we'll define our source in cylindrical coordinates, the angles theta and phi. That'll tell us what direction the wave is coming in. We will need to know the amplitude of the different polarizations. What's the complex amplitude of the TE polarization, and what is the complex amplitude of TM polarization? And I say complex because they could be out of phase with respect to each other. For example, a circularly polarized wave, I would probably set each one of these to 1 over the square root of 2, but then I would also multiply one of them by j. We also need to know the wavelength of the simulation. So this all appears in the dashboard. Then we do our algorithm, and out comes what gets reflected and transmitted. And we have some work to do in the algorithm for sure. Let's think about how we store the scattering matrices. We always seem to talk loosely about the scattering matrix, etc., and it sort of implies that we're going to store the scattering matrix as one big matrix. But in fact, that's not correct. We want to store the 4 things separately because we're always using the elements separately. If we stored it as one matrix, we'd constantly having to be pulling out quadrants of that matrix, sticking them back in. So we don't do that. We just store S11, S12, S21, and S22 as separate matrices in and of themselves. We never ever actually put them together and have an overall scattering matrix. The rare times I've done that, it's because I'm doing something like my code's not working, I'm making sure my scattering matrix is unitary and checking for that, but the overall scattering matrix is never used. It's just the individual elements that are. So we store them separately. Now, how do we initialize the global scattering matrix? Well, we'd like to start off with a scattering matrix of nothing. So we got to ask ourselves, how does nothing scatter waves? So what's the ideal properties of nothing? Well, the first thing is nothing should transmit 100% of the power with no change in phase. That implies that our S12 and S21 parameters have to be the identity matrix. Well, nothing would not reflect. So that means our S11 and S22 parameters all have to be zeros. So if we put all this together, here's what our global scattering matrix would look like after we've initialized it. Now remember, we're storing all these elements individually, but on this slide here, we'll draw them all together. One important thing to note, though, is that is not the identity matrix. Look at the positions of the zeros and the i's. If this were the identity matrix, we'd have smaller 2x2 identity matrices going down the diagonals, and the zeros would be on this other diagonal. So don't make that mistake. Let's handle what we choose for the gap medium. Yes, in principle, anything's possible, but there will be some points where our transfer matrix method could fail. So with a proper choice, we can prevent that. So here's where we start. This is now our analytical solution for analyzing a medium, and I've applied this to our gap medium. I'll point your attention to this equation. We have the difference of two things. We have this mu times epsilon, and then we're subtracting our kx squared and ky squared. So anytime we have the difference of something, there's the opportunity that this could go to 0, and then our kz goes to 0, our eigenvalues go to 0, and it turns out transfer matrix method fails if there's ever a kz that goes to 0. Now, if we didn't care about this, what you'd see is a one little failed point in the middle of your simulation, and not normally such a big deal, but if we can make a more intelligent choice of the mu and epsilon to prevent that from happening, why not do that? So that's the whole trick here. We would like to prevent the z component of the wave vector in our gap medium from going to 0 that would make transfer matrix method fail. So here's one convenient choice. We'll just make the relative permeability of the gap medium 1, and we will choose this expression for the relative permittivity in the gap medium. With that choice, here's what our Q matrix looks like. Simplifies a little bit. Our eigenvector matrix for the electric fields, that's always the identity matrix. And then our eigenvector matrix for the magnetic fields is just minus j times this Q. I'll make a final note. I promise I won't say this anymore, but all the W's in transfer matrix method are identity matrices for when we use isotropic materials. So the W's aren't even used in the transfer matrix method unless we're handling anisotropic materials. I alluded to this before, but let's talk about this again. So here's our expressions for how the fields relate to the mode coefficients through these eigenvector matrices of the electric fields. Well, we just said all of those W's are identity matrices. So it turns out the mode coefficients are the fields. They're the same thing in the transfer matrix method when we're handling isotropic materials. Now later on, when we get to rigorous coupled wave analysis, method of lines, of other things, this is not true. The mode coefficients are not the fields, and that's because the eigenvector matrix of the electric fields are not identity matrix. So the mode coefficients are the fields. That's very convenient. Now we need to talk about calculating this x vector. This is the matrix exponential of our eigenvalue matrix. So here it is. We have an exponential of this omega matrix, but now it's diagonal. And so that's really easy to do. We just apply the exponential to the diagonal elements. So let's say we have our omega matrix, which was a diagonal matrix, and we're in MATLAB, and we just calculate the exponential of that. That's not going to work, right? Here's our omega matrix. This is what we get. And notice what happens to these off-diagonal terms. They're not zeros, they're ones. And that's because the exp function is calculating the exponential of every element in that matrix. And so e to the 0 power is 1. Well, this isn't correct. We only wanted to apply that exponential to the diagonal elements. So one way we can do that is use the expm. This is a matrix exponential. Now the matrix exponential is not just going along the diagonal and doing the exponential. In general, you can have a matrix exponential of a full matrix, and it's doing other more sophisticated things. But with a diagonal matrix, in the end, that's what it would do, and you would get the correct answer. Another thing that you can do is extract the diagonal from omega, call the standard exp function on that. This now gives you a one-dimensional array of all the diagonal elements of omega with the exponential applied. Call diag again, and that makes it a diagonal in a matrix. Now, even though the expm over here looks cleaner, and I've tried it, and it seems to work most of the time, I have had troubles with it, and I find this other approach to be a little bit more robust. So this is what I recommend doing in MATLAB. Now, if we look at calculating the scattering matrices, remember for a layer, we have symmetric scattering matrices, so we only have two big ugly computations to do. But these two computations actually share a term. And so why calculate that big mess twice? Let's calculate it once. So what we'll do is we will set this expression and call it D. And of course, we'll need to calculate our A, our B, our X. We calculate this expression once and call it D. And now when we calculate our scattering parameters, that's a lot more efficient. I mentioned it before, but for transfer matrix method, these speed improvements aren't really that significant because it's so fast anyway. But when we start applying these techniques to rigorous coupled wave analysis, method of lines, when our scattering matrices get much larger, these actually are quite expensive and slow computations. So anything we can do to speed them up is good to do. Let's do the same thing to our star product. Well, here's our star product. Here's our 4 equations for calculating the Redheffer star product. The 2 in red here, these are the same expression. Let's not calculate it twice. The things in blue, that's the same expression. Let's not do that twice. So perhaps a more efficient way to calculate is to calculate an intermediate D and F. These have no physical meaning, but it makes our calculations down here a bit more efficient. There's one confusing thing about implementing the Redheffer star product that I want to mention. So down below, let's say we're updating our global scattering matrix. So we do a star product of our global scattering matrix, star, and then the current scattering matrix of a layer. Here's how we're looking at our updates. First, we'll update S11, S12, S21, S22, and everything works out just fine. What if I decided to reverse the order? And this is something we do when we talk about the reflection side and transmission side scattering matrices. We have to be careful. It turns out we need to reverse the order that we're calculating. So we're going to calculate S22 first, S21 second, S12 third, and then S11 last. Why are we doing that? Well, if we did this equation last, it has a reference to S12 in here. Well, if we were calculating these in reverse, we would have changed our value of S12. This is now the new value of S12. We would be using the new value of S12 here instead of the old value, and that would result in an error. So the answer is to reverse the order. First we calculate S22, then S21, then S12, S11. So be careful of that. Easy thing to trip up. Can the transfer matrix ever fail? Well, we did a fix inside our gap medium by choosing the mu and epsilon of the gap medium so that Kz doesn't go to 0. But you know what? This could happen in one of the layers. The permeability and permittivity of one of the layers at some particular frequency might be just right that the Kz goes to 0 and the transfer matrix method fails. That I know of, there's not really a fix for this, and it's even a physical thing. If we try to use a device where that vector would go to 0, that device has a very touchy response, and we don't typically ever operate around there. Well, I've thrown a whole bunch of stuff at you, so let's tie all this together into a block diagram and show you really how simple this is. So we will start our method. Hopefully we know what we're simulating, we know all the dimensions, we've defined all this in the dashboard, so dimensions, material properties, and our algorithm is ready to begin. The first thing we'll do is calculate the transverse component of our source wave vector. And these kx and ky, they're going to be the x and y components of all of the wave vectors throughout the entire device. So we'll just call those kx and ky, and they apply to everything. Now those are normalized wave vectors, so we don't see a k0 over here. I'm not sure if you noticed that, if that was bothering you, but that's not there because we're using normalized wave vector components. At this point, we'll calculate our parameters for the gap medium. Remember, we had a special choice of mu and epsilon that will prevent Kz from going to 0, and our parameters for the gap medium reduced to this. And we'll be using those parameters when we get into the main loop and we're calculating all of our scattering matrices for the individual layers. Before going into that main loop, we're going to initialize our global scattering matrix. and we set S11 and S22 to 0 because we don't want this to reflect, and we set our S12 and 21 to the identity matrices because we want 100% transmission with 0 phase. This was sort of the scattering matrix for nothing. Now we enter the main loop. So for each layer, the first thing we're going to do is calculate a bunch of parameters for it. So we'll calculate the Z component of the wave vector in that layer. We'll build the Q matrix. We'll build the omega matrix. And then we'll also calculate the eigenvector matrix for the magnetic fields. Remember, we don't need the eigenvector matrix for the electric fields because that's always the identity matrix. Once we have all those parameters, now we can calculate the scattering matrix for that layer. Given the scattering matrix for the layer, we update the global scattering matrix with that layer. And we keep repeating this until we go through all of our layers. At this point, we have what we call our device scattering matrix, and it's all of the layers of our device, but our device is now residing inside the gap medium. So we actually now have to connect it to the outside world. That's our next step. So we'll calculate the reflection side scattering matrix, transmission side global scattering matrix, 2 more calls to the Redheffer Star Product, and now we finally have the final global scattering matrix from which we can calculate transmission and reflection. This is a good point to calculate the source. Sometimes, if I'm in the right mood, I will also do that when I'm calculating these transverse wave vector components, and I'll call it a step that says calculate everything about the source. But technically, the polarization vector is not needed until after the main loop runs. So this is where we'll calculate it. Now we can calculate the transmitted and reflected fields. So that's the source or the incident fields times our S11 or S21, and we get reflected and transmitted fields. That's only the X and Y components of those fields. We need the Z components on the reflected and transmitted side. Now we know all 3 components of the electric field on the transmitted and reflected side, so we can calculate transmittance and reflectance. And we're done. We might want to do other things like add those together, look for conservation of power. Given that block diagram, the last thing I'll mention is how do we handle 0 number of layers? And that actually is useful. We might define some medium on the reflection side, some medium on the transmitted side, and we just want to look at transmission and reflection from a single interface. So that's a 0 layer problem. So what we'll do, when up in our dashboard or wherever we're building our device and we define these 3 one-dimensional arrays that have the permittivity, permeability, and thickness for all of our layers, we'll just make those empty arrays. We'll make our main loop look something like this. First, we'll get the number of layers. Well, L is our 1D array of thicknesses. If that's an empty array, n lay comes back being 0. Now our big for loop for n lay, number of layers, equals 1 to total number of layers. Well, if this is 0, this loop will not run at all. In which case, the global scattering matrix after this loop is still just what we initialized it to. So that's the nothing scattering matrix. So at that point, we connect it to the outside world, and now it's a scattering matrix just describing that one interface. And that's a really useful thing to do.
From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.